Good day, learners. Welcome to Technical Sciences lesson. My name is Zamisile Mdima. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. So today we're going to be looking at mechanics revision. We are combining all the lessons that we've done together on the type of forces, on determining the resultant force, on all the mechanics topics that we've done this term, and we are summing up nicely by using a past question paper that you and I are going to go through together. Okay, so let's get on with it. So our main focus today is going to be on mechanics. Like I said, we're going to be looking at the strategies on how to answer the MCQ questions. Okay, how best can we answer them effectively? 2, we're going to be looking at how to answer long questions, and that includes the problem solvings, the calculations, all the long questions that you will find in your question paper. Okay. Lastly, we're combining the MCQ and the long questions so that we are able to solve all the problems that we are going to come across for the chapters that we have in our ATPs this term. Okay. So, as usual, we have our prior knowledge during any lesson that we're going to have. So, right now, what is it that we should be able to do or able to understand and grasp? So, first things first, we should be able to understand the concepts of vectors and scalars, know their definitions, but most importantly, know how to graphically represent that is the vectors in diagrams. Remember, your vectors have to have magnitude and have to have direction. Okay, so 2, we have to know by now the kinds as well as the types of forces, your contact forces as well as your non-contact forces. Okay, be able to differentiate between the contact forces and your non-contact forces. Number 3, sign conversions, which are very important, representing now your vectors using your Cartesian coordinate system, whether you're using your compass direction or whether you're using your bearing, whichever that is given to you so that you are able to manipulate it and use it to your best knowledge. As well as graphs, we have to know which graph is directly proportional and which graph is indirect proportional. Looking at the variables that are there, which one will be on your x-axis, which one will be on your y-axis, and why there's a difference between the direct proportion as well as your indirect proportion. Okay. The next point we're going to be looking at, or whether you should know by now, is the difference between your collinear as well as your coplanar vectors. Okay, you should be able, 1, to define them, which one are collinear, they have the same line of action, whereas your coplanar, they are lying in the same plane. Okay, also to be able to identify them, when you are given such vectors, you are able to see, oh, this one is a collinear, oh, this one is a coplanar. Okay. Determination of resultant force using various methods. So first things up, we have your Pythagoras theorem, we have your head-to-tail method, you have your parallelogram law of forces. So by now, you should be able to know how to use all of those methods to find or to determine your resultant force. Okay, resolution of force into vertical and horizontal component. Okay, so whether the force is horizontally, meaning there's no angle in between the force and the surface, or whether there is an angle between the force that is being pushed or pulled, remembering that the force is a push or a pull. Okay, lastly, we should be able by now to define a frictional force, to differentiate between the 2 types of frictional force, that is your static and that is your kinetic frictional force, and be able to use to apply it on our daily lives, highlighting the importance of friction in our daily lives. Okay, so these are all the subtopics that we've done under mechanics, and today we are all summing it up into one by revising it using past question papers. Okay, so first things up, let's look at your MCQ questions. So we've got question number 1.1. As usual, there's going to be an instruction, which is very important for you to read so that you answer accordingly. Okay, so it says 4 options are provided as possible answers to the following questions. Each question has only one correct answer. Write only letter A to D next to the question number 1.1 to 1.10 in the answer book. For example, 1.9a. So most people make a mistake of writing the whole statement that is there. For example, if you are choosing an A, another person will not write A, but instead write the whole information that is there on point number A, which is wrong. You just simply need to read your question and then implement it accordingly. Okay, so only the number next to then you write your appropriate answer, which is you choosing an appropriate letter. Okay, so let's read the first question. It says the diagram below shows a bricklayer's movement from his home to the construction site. So this is the direction that we're given, and in this case we have the compass direction. Your north, you've got your south, you've got your west, and you've got your east. Okay, and here is the bricklayer's movement. It is 4 kilometers southeast. Okay, now which one of the following correctly represents his movement? Okay, so before you can even go to the options that are provided, you first read the statement, you read the problem that is given to you, you fully understand the question that is asked of you, and then you do it separately so that you can eliminate the distractors. So amongst the 4 possible answers that are given to you, 2 of them are your distractors. Okay, so you need to know which ones are your distractors and then focus on the other 2. Where the other one is wrong and you're the only one, because you got the only one that is correct. Okay, so by looking at it, the options that is given to us, we've got the bearing. They're giving us the bearing. Okay, because all of us can see that that is 4 kilometers. That is the distance that or rather the movement that the bricklayer's movement from home. However, we're not sure about the direction, so we need to get the direction correctly. So for you to be able to do that, you remember, oh, okay, I need to have a reference point. Now, your reference point, remember, we said it is always in the north part of your diagram, of your Cartesian plane. So this is where your 0 degrees will be at, meaning that this is where you place your protractor and start moving in a clockwise direction. Okay, so if this one is 0 degrees, therefore this here is your 90 degrees. Okay, so and then here is the movement or the direction in which the bricklayers moved to. So if you place it here, so obviously this will be your 0 degrees, your 90 degrees, making this to be your 180 degrees, this being your what? Your 270 degrees, and that one where you started being your what? Your 360 degrees. Okay, so obviously by the look of things, your quadrant number 1, your quadrant number 3 and 4 are out. Okay, now we need to know which one falls onto this that is provided. Okay, it could be a degrees from 90 up until 180. So which one do we have here? So obviously your 20 falls in the first quadrant, so it's out. So your 70 falls in the first quadrant because it's 70, so it is before the 90. Then your 250 falls in the third quadrant, so it is out because that is not where the movement is at, and therefore there the correct answer will be A. Okay, because it's 110, so it falls onto this quadrant, and there's no other that falls onto that quadrant. Okay, so we'll circle out nicely because we have space on this one. Okay, so let's look at question number 1.2. This one is exploring the graphs. Remember, by now we should know a directly proportional graph, and we should know the indirect proportional graph. Okay, so it's always between the 2 variables, whether as the other one increases, the other one increases, or as the other variable increases, the other variable decreases. Okay, so on your direct proportional, both variables increase by the same factor. Okay, whereas in your indirect proportion, okay, some books can say your inverse, okay, proportion, which is one and the same thing. So whether they say your indirect or your inverse, they're talking about the same thing. So in your indirect, or rather the inverse, as one variable increases, the other one decreases, okay, giving you a graph that is either sloping down or sloping up, okay. So let's look at the questions that there is. That is us reminding each other of where to focus on. Two physical quantities, x and y, are directly proportional. Okay, so we are told that x and y are directly proportional. Which one of the following graphs represent this relation? Okay, so a direct proportional will give you a straight line. So as we're looking at this one, okay, this is the one. However, let's check the others if we are not missing anything. It's not your B, it's not your C, it's not your D. Therefore, the correct answer is what? It is A. Okay, because as this x-axis increases, the y also does what? Increases. Therefore, showing a direct proportion between, or rather, a direct relationship between the two variables. Okay. Question number 1.3. Two workers applied forces F1 of 8 newtons and F2 of 6 newtons. So they gave us a nice diagrammatic representation for us to see these two workers, or rather the forces that are exerted by these two workers, okay, to a concrete block as shown in the figure. F1 is perpendicular to F2. Now, the magnitude of the resultant force experienced by the block can be used by finding, okay, is it the sine rule? Is it the Pythagoras theorem? Is it the cosine rule? Or is it triangle law? Okay. From the list provided, or from the possible answers provided, we can tell that we haven't talked about sine rule, we haven't talked about the cosine rule or the triangle rule. So the one that will apply is your what? Your Pythagoras theorem. Okay. So the correct answer in this case is B. 1.4, the figure below shows two vectors P and Q, okay, acting on an object. They have the same line of action. Same line of action already. I will underline that statement if I were you, because it gives me the solution. It gives me the answer, okay. P and Q are therefore called what? Is it A, coplanar, B, collinear, C, parallel vectors, or D, concurrent vectors? Don't forget the distractors that I told you about. So, parallel vectors, concurrent vectors are your distractors. Okay, so you're looking for either A or B, which is your coplanar or collinear. And therefore, we're going back now to the definitions. Okay, what is a coplanar vector? It's the vectors that have that are lying on the same plane. Okay. Collinear vectors, on the other hand, they have the same line of action. So, in fact, that statement that they provided to you is the answer, because it is the definition. Okay, so the correct answer you're looking for in this case is your B. 1.5, okay, on the frictional surface, it is easier to keep an object sliding down than it is to cause it to start sliding. Now, this is because of what? Remember, we're talking about now frictional force. It is easier to keep an object sliding, okay? You're keeping it sliding, or rather cause it to start sliding. This is because why? So, what are these that are represented here? So, let's first start by identifying which one are your distractors. Your C as well as your D are your distractors. Why? Because we are concerned about the coefficient of frictional force, okay, which is the one that is telling us about the surface, whether it is smooth or whether it is rough. Remember, the rougher the surface, the more friction that you will experience. Okay, so the correct answer in this case, your static friction has to be greater than what? Your kinetic, or rather your kinetic frictional force, or your kinetic coefficient kinetic frictional force. So this is the first one. Why? Because your mu s, which is standing for the coefficient of static frictional force, is in this case greater than coefficient of static frictional force, is greater than your what? Your mu k. Now, on to the long questions. Question number 2. It says, displacement of two learners, Sia and Tando, are shown on the Cartesian coordinate system. So we are shown the coordinates, the Cartesian coordinate system of both Sia as well as Tando, okay? And then Sia traveled from point A to B, and Tando traveled from P and Q. Now they've used the scale of 1 meter apart from each point, okay? Meaning moving from number 1 to number 2 is your 1 meter, okay? So what is the distance traveled by Sia? So remember, your distance is your scalar quantity. That means it only have your magnitude only. There is no direction. So since they are asking you about the distance, you'll have to give us the magnitude only. Okay. So you go to a Cartesian coordinate system for Sia. Okay. And then now you say Sia move from here, from point A, which is at number 1, to point B. So you said this is my 1, this is my 2, and this is my 3. Okay, so the distance that is traveled by Sia is therefore 3 meters. Okay, why are we using this unit? Okay, it's because we are told right there then the one main scale division is equal to what? 1 meter. Okay, telling us that it is, the numbers are 1 meter apart. Okay, the second one, which is your 2.1.2, what is the displacement of Tando? Okay, take into consideration now that the displacement is your vector quantity. Therefore, I need to give the magnitude, and also I need to give the what? The direction. Okay, I got to the Cartesian coordinate system for Tando, and I said, okay, moving from point P to point Q, what is the displacement? So you said 1, 2, 3, 4, 5, 6, 7. Okay, so that means it is 7 meters. And in which direction is Tando moving? Tando is moving to where? To the left. Okay, so one person can use left, or you can use west. Moving right along, you've got 2.2 now. We're done with your 2.1. It says 2 construction workers are pulling concrete block by using a long rope as shown in the figure below. Worker 1, okay, exerts a force of 130 newtons, and worker 2 exerts a force of F2, which is equals to 70 newtons. Okay, so now they gave us a nice diagrammatic representation. They are both pulling the force. Use your worker 1, which is with a force of what? Of 130 newtons, as well as your F2 with a force of 70 newtons. Okay, first questions and saying define the resultant vector. Okay, it goes back to your definition, which is very important. What is a resultant vector? Okay, so this is your 2 point. Let's go back a little bit. So this is your 2.2.1. So your 2.2.1, we are defining a resultant vector. Okay, so you need to remember that it is a single vector that has the same effect as 2 or more vectors that are acting together. Okay, so it is a single vector that has the same effect as two or more, because it could be two or more vectors acting together. Okay, so remember your definitions are very important because they allow you to be able to calculate, for instance, in this case, your resultant vector correctly. Okay, so now if you don't know how to define, chances are you wouldn't be able to calculate the resultant vector because now you lack that understanding or that proper definition of what a resultant vector really is. Okay, let's go back to our questions, and then the following question, which is our 2.2.2, it's saying using a scale diagram. Okay, a scale diagram. That means this diagram needs to be drawn to scale. Okay, using which scale in this case, here's your 20 newtons is to 10 millimeters. Okay, using a scale diagram, find the resultant force experienced by the block. Okay, so how do we then, let's remind each other, how do we then use a scale diagram? Okay, and also how to best utilize the scale. Okay, because now we do not have that 130. We can't draw that 130 in a piece of paper. Okay, so let's look at how we can best be able to answer this question effectively. So we're looking at question 2.2. Let's start with the scale. So your scale is saying 20 newtons is to what? Is to, okay, let me write it nicely, is to 10 millimeters. Okay, then you ask yourself, let's start by doing the first force, your F1. Okay, and then you say to yourself, okay, I have 130 newtons, but how much in millimeters, the distance that I should draw in a piece of paper? Remember, your scale allows you to be able to reduce or magnify the drawing. Okay, so depending on the scale that you are doing, in this case we're just trying to reduce so that the line that is representing the force is be able to drawn in a piece of paper. So you have a 130. So in this case we have 130 newtons, and what is it that we're trying to find out? We're trying to find out in millimeters the size or the magnitude of this force that we're going to be able to draw. So I put an X over there because that is what you're trying to find out. Okay, so because these units are the same, you're going to cancel them out. Okay, they cancel each other out. So now you are going to do a cross multiplication. That means that you're going to say, let's use a different pen so that you're able to see what we did. 20 times X is going to give us 20X. And then you've got now your 130 times 10. Okay, therefore this is equals to how much? Then you put that into your calculator. You said, okay, what is now my 20 times, your 130 multiplied by 10? You get your 1,300, because the only units that you're left with now, it's millimeters. And then you write your millimeters. Okay, we're not trying to find 20x, we're trying to find x. Okay, so we have to divide by 20 on both sides, so that this 20 cancels that, and then x is going to be equals to 1,300 divided by 20 is going to give us 65 millimeters. So in your piece of paper, this is the magnitude that you're going to draw. However, then after you've drawn it, when you are labeling your vector, you use the original labeling so that we know this is our F1 and this is our what? Our F2. So let's do it together. Okay, so this was just me showing you how to best use your scale so that you know how to reduce or to magnify your drawing, okay, or rather your diagram. Okay, so the question has asked us, so we had like two of them. we had 130. So we're going to make this one bigger. So this is your F1. Okay, where am I taking this diagram from? It is taken from here. Okay, now remember your 130 newtons is bigger in magnitude as compared to your F2. So your F2, you show it even with your the lines that you are drawing. So the magnitude counts. Okay, so that is why you have to draw it in scale. Okay, the next one is your F2. However, because they are both being pulled to the east, they have to show the direction that both of them are going way to the east. Okay, so your F2 as well, we are doing the head to tail now. So this is your F2. Okay, which is 70 newtons, and then the first one being what, your 130 newtons. Okay, so you may be asking yourself, then why, ma'am, did you do all these calculations? Because now your F1 was in magnitude 130, but you have reduced it to not draw 130, but draw what? 65 millimeters. Okay, however, when you are doing your labeling, you said, okay, my F1 originally it was what? Your 130. But in the drawing, you have reduced it using what? A scale. Okay, so these are the two forces. Same thing, you do the same thing on your F2, which is your 70 newton. Okay, and then you reduce it so that you know how much you should be drawing in your piece of paper. Okay, but don't forget, when you are labeling it, your F2 still remains your what? Your 70 newtons. Okay, so now we need to draw the resultant force. Okay, now your resultant force is going to be going like this. I'm going to use a red line so that you are able to distinguish it. So here is your FR. Okay. Now, what is the magnitude of my FR, you may ask yourself. Okay, we have implemented in this case a head to tail method, because where the head of F1 is ending, I have joined the tail of F2. Okay, so now FR, in which direction is this going to go? Am I even right to point it in that direction? Now let's find out. FR, therefore we say FR, F1 plus F2. Okay, so both of them are both of these vectors are going to have the same sign. Why are they having the same sign? Because they are all going in the same direction. Both these two workers were pulling in the same direction. So in other cases whereby you have one worker pulling to the east and other one that is pulling to the west, therefore we'll have one positive and the other one being what? Being negative. Okay, so also the magnitude of those forces will count, because the one with the bigger magnitude, then you give it a positive sign, and the one with a a smaller magnitude, then it gets what? A negative sign. So in this case, they're both going in the same direction. They both get the same sign. So you've got your 130 plus, let's just, because this one looked like plus. Okay, our plus needs to be a decent one. 70. This is going to give us 200 newtons. Okay, so therefore this is our FR. So it's giving us the positive number, so it's also going way to the east, because we had taken the east side as positive. That is how easy it is to write the scale diagram, okay, and representing FR. Therefore, you said, okay, this is my FR, which is equals to 200 newtons, okay, to the east. Okay, that is how easy it is. Moving right along, let's look at your 2.3 now. We are talking about two men who are exerting a force on the block of bricks from two buildings. as shown below in the figure below. So the man on building 1 lifts the brick upwards with a force of F1, which is equals to 118 newtons. And then we have the second man, the other man on building number 2, pulls the brick horizontally with a force F2, which is equals to 80 newtons. Okay, so you've got 2 men who are on separate buildings. The other one is pulling on the other side, and the other one is pulling on the other side. Okay, so first question, before you even get into the question, this is a very nice diagrammatic representation, okay, to show you whether the vectors that they are talking about are coplanar or are collinear. Okay, so you look at your vectors, you're like, okay, here's men number 1 and men number 2, and their forces that are exacting onto the block. Okay, you said the first question is saying 2.3.1, define the coplanar. So it's the vectors that lie on the same plane, meaning the other one can be going horizontally and the other one can be going vertically. Okay, so they don't lie on the same line of action like your collinear, but these ones have the same plane. Okay, so define it. I just define it over here. Vectors that lie on the same plane. And that is your full 2 marks. Okay? 2.3.2. Name one non-contact force and one contact force in above diagram. Remember now, you have 2 kinds of forces. Okay? In your kinds, you've got the types. Okay. Now, name one contact force and one non-contact. So this is us trying to remind you of that, being able to define a contact and non-contact force. Remember, with your contact force, you have to come in contact with the object that you are coming or you're exacting a force on. Okay, so in that case, your non-contact force, which is your 2.3.2, let's write it over here so that you can see non-contact that means you don't come into contact. You don't even touch it. You don't touch the object you're exacting a force onto. So what type of force can that be? Your gravitational force. I can let go. If I let go of this remote, it won't fly out of the window, but it will just go down. Why? It's because gravitational force is pulling it down with a constant acceleration of what? Of 9,8. Gravity didn't have to touch this object, but it's there because the object will be pulled downwards. Okay, so this will be your gravitational force. And then one example as well of your contact force. Let's go back to the diagram so that you are able to identify it with me. So, this block is therefore being touched by who? The builder number 1 and builder number 2, which are exacting a force of F1 as well as what? Your F2. Now, because they're applying a force by pulling this block, so the forces that is F1 and F2 are in contact with the block. Okay, so therefore it can be F1 or F2, or you can just say applied force because they are applying a force onto the what? Onto the block. Okay, so that's how easy it is. And then let's look at your 2.3.3. It says now, calculate the resultant force acting on the block of the bricks in the vertical direction. So we're looking for the vertical direction, which is your y-axis, okay? Therefore, we want the resultant of all the forces that are acting onto the vertical direction, because they specifically said the vertical direction, okay? Let's look at the diagram. So in the vertical direction, you have got F1, which is acting at a 90 degrees angle to what? To F2, okay? So now, this one, we need to calculate what? Because it's acting at an angle, we need to calculate what? The vertical component of our F1. 2, if we're looking at the downwards direction, we also have the force of gravity that is acting onto the block. Remember, we have counted force of gravity as a non-contact force. It is there, but it is not touching or having a physical relation to the block, okay? So, we start going to be saying the F1, but we're finding the y component. So we're going to say is equals to F1 sine of theta. Why are we using sine? It's because we're looking for the vertical component, okay? So what is the magnitude, we ask ourselves? What is the magnitude of F1? Let's go back there. It's 118, okay? So 118 sine of 90 degrees. Now we do know that 90 degrees is 1, okay? So multiplying it by 118 is going to give us what? 118 Newton, okay? You can simply put everything in here into your calculator. You say 118 sine of 90, therefore it gives you 118, okay? But now we're still calculating the vertical component of the F1, the vertical component of it. And therefore, now there's force of gravity. We know that it is Fg. It's a gravitational force is equals to mg. We say, okay, what is now the mass of this? Let's go back into it. So we are told that it is what? It is 10 kg, okay? And g represents the constant gravitational acceleration of all the objects that are inside Earth, okay? So this is your 9.8 meters per second squared, okay? Therefore, 10 multiplied by 9.8, this is your constant, okay? So it's going to give you your 98 newtons, okay? Bear in mind that these forces are acting in what? In the vertical. However, the other one is going up, the other one is going down. So both these vectors are in opposite direction. One has to be positive and the other one has to be negative because they are vectors, so direction is very important, okay? They asked us about the resultant. So here we are. Therefore, FR is going to be equals to, remember the bigger one we said, okay, because it's bigger, we're going to give it the positive sign, and the one that is smaller, we're going to give it what? The negative sign. So we're going to have F1y and then plus FG. However, our FG, because it is smaller, we're going to say it is a negative FG because it is also in the opposite direction. Okay, so into negative gravity. So what is our F1y? I'm calling it F1y because this is the y component. Okay, so this is 118. Positive times negative will give you a negative. And then so this is going to be negative 98. Okay, So what is it? Therefore, your 118 minus your 98 is therefore giving you 20 newtons. Okay, and I had said to you, if your answer is positive, you go back and said, which side did I take as positive? Okay, in this case, you took up as what? As positive. And your answer came as positive. That means your resultant force is 20 newtons upward. But if you had taken up as negative and then your answer comes back as negative, that means your upward is your resultant force is what? Is negative. So here your positive and your negative is a clear indication of the direction. Okay, because we are dealing with forces which are what? Which are your vectors. Okay, so what were we answering to? We were answering in 2.3.3, which says calculate the resultant force acting on the block of bricks in the vertical direction. That is why it is worth 5 marks, because there's a lot of work that you need to do before you find the correct answer. Now we are on 2.3.4, which says now calculate the magnitude of the resultant force acting on the block of brick. Okay, the resultant now, the sum of all the forces that are acting onto this brick now, not only in the vertical direction, but all the forces that are acting onto it. Okay, I want to go a little bit into the diagram so that you can get a feel of what we're talking about. So we have calculated the resultant on the vertical direction. Now we need to even include F2, because now it is a force. F2 is a force that is being exerted onto this block. So if we have to find the resultant force, we already know the resultant force for the vertical direction. Now we need to be able to find the resultant force for all the forces that are applicable into this block. Okay. Okay, let's try and find some space in here, which is your 2.3. Let me just write using another pen, which is your 2.3 what we're doing 4. Okay, so now the upward movement or the vertical direction, we already have it as 20. So we can use it by using the Pythagoras theorem, meaning your FR squared is equals to your I'm going to call it Fx, because we have an x and a y now. So you're going to have an x squared plus Fy squared. Not forgetting that the y, because the vertical direction we already counted or found the resultant of all the forces that they're acting on the vertical direction. We got it as what? As your 20. So this is 20 squared. And here, just to go back and remind you, your F2 is what? Is your 80 newtons. Okay, so over here, you've got your 80 squared. Not forgetting this is still your FR squared. Okay, so you're going to have your 80 squared plus your 20 squared, which is going to give you 6,800. Then square root of 6,800 is going to give you, therefore your FR, because this smaller space in here, is going to give you 82, 46 newtons. Okay, so that is how simple we're finding it. So let me just go slowly. This is on your x-axis, which is your 80. This is on your y, which is the resultant of the vertical direction, giving you 20. And then it's 20 squared plus 80 squared, sorry, plus 20 squared is going to give you 6,800. But that is still your FR squared. You introduce a square root on both sides. What you do on your left is what you're going to be doing on your right. And then so that this squared is then removed by the square root. And therefore you are left with 82 0.46, which is the square root of what? Of 6,800. Okay. Question number 3. So, if we go back a little bit on this question, we've explored so many things on the slide alone. We've explored the kinds of forces. We've explored the components, resolution of a force into vertical and horizontal component. We've also explored the determination of the resulting force by using the Pythagoras theorem, all in one go. Okay, so that was a good exercise. Question number 3. Diagram 1 below shows a rope tied to 2 poles so that it is horizontal. Now, diagram 2 shows an iron ball of mass of M suspended from the same rope. So, in diagram 1, it's just a rope tied on both ends. And then diagram number 2, now we've tied what? A ball, an iron ball of mass M from the same rope so that it sags, okay, creating an angle, okay, on both sides. So the first question, 3.1.1, calculate the vertical component of tension 1. So here's your tension 1. What is this question trying to remind us of? It's trying to remind us of the vertical and horizontal component, how to do resolution of a force into vertical and horizontal component. So if we were to close this up, this will give us the horizontal and this will give us the vertical component. Okay, so we want the vertical component to be specific of tension number 1. Okay. That is your 3.1, 3.1.1. We say, because we're talking about tension number 1, we're going to say we want to find FT1Y. Tension force on 1, the vertical, okay, is equals to FT1 sine of theta. So, what is the magnitude then? Let's just go back a little bit. The magnitude of tension 1 is 5 newtons, okay? And it's acting at an angle of 18 degrees. 5 newtons acting in an angle of 18 degrees. So this is going to be 5 then sine of 18 degrees, okay? They put it as it is. 5 sine of 18 degrees is going to give us a 1,5 Newton. So this is our FT1Y. Okay. Let's go back. So we've answered our 3.1.1. That is how easy it is. Let's continue with our questions. 3.1.2. Calculate the vertical component now of tension 2, T2 that is. So, not only did we had to calculate the vertical component of this, but also now we have to calculate the vertical component of T2. So it's 7 newtons acting at 20 degrees. 3.1.2. FT2, in this case y, is equals to your FT2, which is your original force, and then sine of theta. So therefore, it is 7 sine of 20 degrees. Why do I have those values? Because they are given to us. Okay, let's just go back just to show you here. Here is your 7 newtons acting at an angle of 20 degrees to the horizontal. Okay, so you said, okay, what is now my 7 sine of 20? It's going to give us a 2,39. 2,39 Newton. That is your Ft2y. Okay, that is how easy it is to find your vertical component. So we've resolved a vertical component for T1 and we've resolved a component for T2. Let's go back to your question on 3.1.3. Calculate the resultant of vertical component of T1 and T2. Now, see this. We want now the resultant of vertical components T1 and T2. Okay, so you want the single vector that has the same effect as both of them combined. Okay, so what do? We say now 3.1.3 FR, because we want the resultant vector now, is going to be equals to Ft1y plus, remember, because now we were calculating the vertical components, so both of them are going up. They're on the vertical, okay? So they have the same direction, meaning we're going to grant them positive, okay? Plus Ft2y. So what was the value of our vertical component for T1? It was 1,55. So 1,55 plus 2,39. So 1,55 plus 2,39 therefore gives us a 3,94 newtons. So this is the resultant of the vertical components. Okay, this is how easy it is. Okay, so because we are asked about calculate the resultant of vertical component for T1 and also T2. 3.1.4 says now hence calculate the mass m of the iron ball. The iron ball that is sagging. Let us look at the diagram that is sagging over here. Now we know the resultant that is going up. What is the mass of this? Remember, the mass is going down, whereas the vertical component is going way up. Okay? So now, what is the force? We ask ourselves, what is the force that is acting onto this ball? Okay? So we know that it is not in contact with anything, but we do have non-contact forces. Therefore, there is a force that is acting onto this block, what we're calling it an iron ball, and it's your gravitational force. Okay? So, 3.1.4. Therefore, your F, I'm going to call it FRV. I'm going to tell you why I'm saying that. RV, okay? It's a resultant force of the vertical components, okay? So FRV in this case is equals to what? FG, which is going downwards, okay? What is the value of our FRV? It is, before we even get into the value, let's try and expand. What is FG? Okay, we know FRV is equals to mg. Now, let's go into our substitution now that we know that FG is equals to mg. So FRV is 3,94, which is equals to, what is the mass of the iron ball? We have no idea, okay, because this is what we're trying to find out. We're trying to find the mass m of this iron ball. So it is m, but we do know the constant gravitational acceleration of the gravity is 9,8. Therefore, we divide by 9,8. on both sides, and voila, we have our mass. So we are left with m on this side, 3,94 divided by 9,8, therefore gives us a 0,40. 0,40. We don't leave it like this. We say therefore m is equals to 0,40 kg. That is how easy it is to find the mass of the iron ball. Is there any other question we left behind? No. So we may proceed. 3.2. A steel beam is supported by two ropes as shown below, which is your T1, which is equal to 70 newtons, and T2 as 50 newtons. Okay? And are the tensions on the ropes, and the angle between the ropes is 50 degrees. Yeah, that is the angle between the two ropes. The first question, before we even get into the question, let's look at the diagrammatic representation. So you've got your T1 having a magnitude of 70 newtons. You've got your T2 having a magnitude of 50 newtons. Okay, they are separated by an angle of 50 degrees. Okay, so 3.2.1 states the parallelogram law of forces. Okay, so you need to be able to state it so that you are able to calculate using the parallelogram law of forces. So what does it say? So if the two forces are acting at the point, okay, then these ones can be represented by the two sides of the what? Adjacent sides of the parallelogram. Here's my side of the parallelogram. Here's my side of the parallelogram in magnitude as well as what? In direction. Okay? Now, the diagonal from the point of action therefore represent the resultant of the two forces. Okay? Let's write it down. 3.2.1. Parallelogram law of forces. If two forces acting, okay, at a point can be represented by the adjacent layer, by adjacent sides of a parallelogram in magnitude and direction then what does that mean? The diagonal then from the starting position point represents now the resultant of the two forces. I know it's long, of the two forces. Okay, because it's a law, it needs to be stated correctly. It's 2 marks or nothing. Okay. 3.2.2. Use the parallelogram law of forces. Now we are applying the parallelogram law of forces to determine graphically the magnitude and direction of the resultant tension of the tension T1 and T2. Okay, so it is very important to use your protractor in this case so that you are able to measure the bearing correctly. Number 2, to be able to use the scale correctly. Okay, for example, you look at the magnitudes that you have for T1 and T2, both of them, and then you say, okay, which scale can I use? All right, I can use a 1:10. Okay, because I can draw 7 centimeters instead of 70, and I can draw 5 centimeters instead of 50 newtons. Okay, now what you need to do there, 3.2.2, you can use a 1 centimeter is to 10 newtons. Okay, I'm going to show you how you do it. So don't forget to measure your angle in between them. So you've got your 50 over, I think you had your 70 first. Yes, you had your 70 first. So you're going to have your 70 over here. Okay, obviously, because you're going to be using the scale, you're only drawing a line of magnitude of 7 centimeters. Okay, and then you're going to have your 50. So let's label them. So this is your F1, which is equals to 70. Don't forget to use the correct bearing that they've given you, which is 50 degrees apart. And then there is your F2, which is 50 newtons. Okay, so you therefore complete your parallelogram. I'm going to use a different pen. You therefore complete your parallelogram, making this side to be equals to that of F1, which is equals to 70 newtons. Therefore, just this is portrayed on this side. Therefore, now you are not writing because this one is a solid line. It's representing your original force, and this side has to be dotted so that it is just a reflection of your F1. And then your F2 then goes up in there. There you are, having completed your parallelogram. So this is the extension of your what? Of your F2, which is 50 newtons. Okay. So let's go back to the definition, or rather the law, and see how did we use it. If the two forces acting at a point, so you will find that your F1 and F2 were acting at a point. Okay, they met each other at this particular point. Okay, can be represented by the adjacent sides. We've represented this, what the adjacent side, which is your F1 side and your F2 side. Okay, both in magnitude and direction, which is the reason why it is so important to use your scale when you are drawing these vectors. Okay, remember I said to you, the scale allows you to magnify as well as to reduce. In this case, we have reduced it so that we are able to draw 5 centimeters for your F1 instead of your 70 newton, and draw 5 centimeters instead of what? Your 50 newtons. Okay, so we've both represented them in magnitude as well as in what? And in direction. Why are we saying that? Because we have the correct magnitude, and also we have the arrowheads, which are giving us the direction. Okay, the diagonal from the starting point therefore represent the resultant of the two forces. Okay, then we take our ruler and then we complete. We write a diagonal straight from the starting point right over to where we've completed our parallelogram. Okay, so in the law of parallelogram, this then represent our resultant force of both F1 and what? And F2. Okay, so how do we then find the magnitude and direction of this one. Remember, your north is remaining your what? Your reference point. So you place your protractor over there, and then you can, in which bearing does it fall into? Okay, so you read your protractor in a clockwise direction, and also this line will therefore give you the magnitude of your resultant force. Okay, don't forget, because now you've reduced it. Okay, you've wrote 7 centimeters. You need also to say the whatever magnitude you are getting, you also need to magnify it to say, okay, because we've reduced it, the ideal resultant force is therefore this one. In this case, you'll be getting using your scale, you therefore write the correct resultant force. Okay, I'm going to make a typical example. Let's say we are finding over here 1, 2, 3, 4, 5, 6. Okay, because I don't have a ruler with me. So how do you write then the correct resultant force? You say, okay, I've just measured 6. Okay, assuming that this is 6, I'm going to say assume the distance that you found for your FR is equals to 6 centimeters. So how do you then use your scale to go back? You say 1 centimeter is equivalent to 10 newtons. Okay, therefore, if I have 6 centimeters, how many newtons do I have? Your centimeters are cancelling each other. Therefore, 1 times x is going to give you x, and therefore 6 centimeters times 10 is going to give you 6 newtons. Therefore, your FR is therefore 60 newtons. Okay, so that's how easy it is to go back using the scale. Okay, now hopefully that was easy enough for you. Okay, let's just find out if we did not leave any other question. No, we did not. Okay, and then before we go from this question, one thing I want you to understand, also don't forget to find your angle, theta. Okay, remember I said to you, this is your reference point, which is at 90, and then you place your protractor, and then you get the angle from where it is acting on. Okay, so that your resultant force have got your magnitude as well as what? As your direction. Okay. Question number 4. A box with a mass of 100 kg is being pulled over a friction surface. So they just told you straight up there's friction involved, with a horizontal force of F is equals to 1,200 newtons. Now we're exploring friction. Okay. As shown in the figure below, the coefficient of friction is equals to UK is equals to 0.2. Now, here's your box, nice diagrammatic representation. You've got a box of 100 kg pulled horizontally by the force of 1,200 newtons. First question, define force of friction. Okay? .1, they're saying force of friction. Okay, what is a force of friction? There are 2 things that are important in mentioning in your definition. It is a force that is parallel to the surface and opposes the motion of the object. Parallel to the surface and opposes the motion of the object. Okay. Let's go back so that we get the questions. and say, draw a free body diagram showing all the forces that are acting onto the box. And that's 4 marks. Remember what we talked about? Marker location equivalent to the number of forces that are acting into the object. Let's see if it's correct. Okay, so we're drawing a free body diagram. Free body diagram, it's free. It has to be a ball. So that's your 4.2. Here is your ball. Okay, because it is on the surface, so there has to be normal force. Gravity. Horizontal force of 100. We're going to call it FA, applied force, and then frictional force. That is how beautiful it is done. So 4 marks, 4 forces, it's still like that. 4.3, calculate the kinetic frictional force experienced by the box. Remember, we've been given the coefficient of kinetic frictional force, not the kinetic frictional force. Okay, so in this case, on our 4.3 now, so what should we do? Remind yourself, what is it that is needed? Fk is equals to mu k n. In this case, because now the block or the force that is acting onto the block is horizontally. Okay, so there's no angle in between them. So that means that the normal force is equals to what? The force of gravity. Okay, so therefore, if Fn is equals to Fg, what is Fg? Fg is equals to mg. Okay, so we expand our normal force that it is equals to what? Fg. Therefore, this is our mu k, and therefore n is therefore equals to mg. Okay, multiplied by mg. Okay, therefore, what is the coefficient of kinetic friction that is given to us? It is a 0,2 multiplied by, what is the, it is 100. The mass of the block, it is 100 multiplied by 9,8. Okay, that is your substitution right there. Put everything in your calculator and say 0,2 multiplied by 100 multiplied by 9,8 is going to give you a good 196 newtons. Okay, beautiful stuff. What will be the magnitude of frictional force if the object is moving with a constant velocity? Okay, let's underline the keywords. Constant velocity. Okay, what will be the magnitude? They're asking about the magnitude of frictional force if the object is moving at a constant velocity. Now, let's have a look. So we have our F being equals to 1,200, which is the applied force. So now, if the object is moving at a constant velocity, that means the magnitude of the forces on either side are equal. Okay, so you have 1,200 and all the forces that are acting into it are equal. So if this object were to move at a constant velocity, that means even frictional force moving into this direction will be also 1,200. Okay, because forces on the left will be equal to the forces that are onto the right. Okay, so for our 4.4, it will be 1,200. So let's just write it in full so that you know what it is. So that means our kinetic frictional force will also be 1,200. 200 newtons. Obviously, because now they are the same, it will be like on the other one will be positive and the other one will be negative. Okay. Let's have a look on the next question. What will be the resultant? Okay. What will be the resultant force acting on an object 4,4 in above? So in this here, what would the resultant if now the object was moving at a constant velocity? Okay. So now, because now we'll have, let's make it a 4.5, will be our FR is equals to FA plus into minus frictional force. But because both of them are of the same magnitude, this is 1,200, which is the applied force, minus what? 1,200 newtons. Therefore, this will give us 0 newton. Okay? Because either of them are cancelling out each other. Okay? The next question, and then 4.6, what will the kinetic frictional force change? Okay, sorry, let me read that right. How will the kinetic frictional force change? Okay. Our main focus is on kinetic and how it will change, whether it will increase, whether it will decrease, or whether it will remain the same. So we are focusing on frictional force. If now force F, which is the applied force, acts at an angle of what? Of 30 degrees. Okay, so how will that change? Remember now, it's not acting onto the horizontal. Now it is acting like that. So it is your F, which is then creating a 30 degrees angle. Okay, so it will decrease. How? Because now your normal force will be subtracted from, let's just do it together. .6. Our kinetic frictional force will therefore be mu k n minus, okay, minus F sine of theta. That means we will not just be able to calculate as mu k times normal force. We'll have to subtract the vertical component, decreasing the frictional force. Therefore, we conclude by saying it will do what? It will decrease. And then, how will the kinetic frictional force change if the mass of the ball increased? Okay, let's put it into practicality again. So we said here the correct answer will be decrease. 4.7. I think this is 4.6.1. And then this is 4.6.2. So we are asked if the mass increased, that is what we are asked about. If the mass of the ball increased, what will happen to the kinetic frictional force? So we say FFK is equals to mu k n. Okay, remember n is equals to mg mu k multiplied by the mass and gravity. So that means as your kinetic friction increases, this one also increases. It is directly affected by the mass. So once you increase the mass of the ball, sorry, in this case we're talking about the block, therefore it just increases the kinetic frictional force. Okay, so in this case we are saying it will do what? Also increase. That is how easy it is. You can use your formulas to be able to understand the relation between the variables that are involved in your formula. Okay. here now is the good time that we all have been waiting for. I know you can't wait to prove yourself that yes, you can do it. You are now got all the strategies to problem solving. You know how to do your calculations correctly. Yes, you thought you know the content, but now you do know the content. Okay, so I'm giving you a nice activity to do so that you put into practice all now the topics that we've summed up together today on this lesson, on this beautiful lesson. Okay, so it's just the similar questions, similar content, but now it has to be different so that I can know that you know how to do problem solving. Okay, so just like we did it, I am going to give you the multiple choice questions, so MCQ questions, so that you are able to identify your distractors, and you are able to eliminate them. Okay, so that you are able to spot the correct answer correctly. Okay, so this is your multiple choice question. I'll go through it with you so that I can highlight what is it that you need to do, just to give you a hint of what should be done. So this is the same way of answering. You just write your number and then your correct alphabet next to the number. So your SI unit for the force, this is very easy. The side next to the angle theta, okay, of a right angle triangle is called, okay. Using the bearing method, the direction of the vector in the diagram below is, so you focus on the vector that is given to you, okay, and you choose the correct answer, okay. Remember that one is in the first quadrant, and also remember how we calculate the bearing, that your north is your reference point, okay. I'm sure this is very easy for you. 1.4 kinetic frictional force is a type of friction in which acts when the object and the surface, when the object is, you need to know the keyword. What does kinetic mean? Okay. Question number 2, here's your long questions. Use the information on the table to answer the questions that follow. So you're given a table of speed and traveling time, okay. So your speed is in kilometers per hour and your travel time is in hours. So in the graph sheet provided, represent the above information in a graph, okay. Remember, you need to know what is your dependent variable, what is your independent variable, okay. Also, okay, let me not give you too much hints, okay. 2.2, does the above information represent a direct or inverse? Remember what we said about the variables that are involved, okay? What happens when it's direct? What happens when it's indirect? Okay, briefly support your answer by referring to the graph or by calculations, okay? You can either use either or, okay? Question number 3, define the resultant, okay? You remember what we said, you can't be able to calculate something you don't know. So first we need to know the definitions and know then how to apply them. Okay, consider the following forces acting on an object. So we've got 2 forces that are just drawn into the block. Okay, not that they are the only ones that are acting onto the block. Okay, draw a free body diagram indicating all the forces acting onto an object. Remember what we said about the Mach allocation, which is equals to, okay, equivalent to the number of forces that are acting onto an object. So there has to be 4, okay. And then 3.2.2, determine the magnitude of the resultant force acting on the object, okay. The resultant of the forces that are acting onto an object, okay. Using the scale 1 centimeter is to 1 Newton, okay, draw a vector diagram to representing the horizontal forces acting on the object above. That is one is very, very easy because we've done it. And then 3.4, a force FA is applied to remove a pin from the ground as shown below. So you're given FA as 500 newtons acting 45 degrees to the horizontal. And then determine the X component, determine the Y component, and then represent the above calculated component in a vector diagram. Okay, so this is just resolution of forces of a force into the vertical and the horizontal. Remember, another word for X component is the horizontal. Another word for the y component is the vertical. So that's pretty much that. Okay, question number 4. Consider the diagram where two forces FA and FB are now used in order to remove the pin from the ground. Okay, the angles of the forces are adjusted as shown below. So you've got your FA now, and then you've got your FB, and they are bearing 50 degrees and then 60 degrees. I have a good feeling this is about to get fun. So determine the x component of FA and FB, the y component of FA and FB. They're still testing you on the vertical and horizontal components. Okay, determine the magnitude of the resultant of the force. Okay, using the bearing method, determine the direction of the resultant. Okay. Question number 5. Two tags boats are used to move a cargo to the shore of the ocean. The force and the angle in which the force is applied by each tugboat is indicated below. The tugboat and the cargo move at a constant velocity. Okay, that's why they give you, I love the diagrams, they give you a clear picture. Okay, and then draw a free body diagram representing all the forces applied by the two tugboats on the cargo. Using the tail to tail parallelogram, okay, or tail to head sketch, not to scale. Draw a sketch representing the resultant of the forces acting onto the cargo, and then lastly, determined by accurate construction and measurement. That means you need to use that 1 centimeter is to 5 Newton scale. Okay, what you're trying to find out is the magnitude of the force applied by the cargo onto tugboats. Okay. Question number 6. We're exploring friction again. Define the following terms. 6.1.1 static. The word static, where does it come from? Okay, that will give you a clue on how to define it properly. Normal force, where is it going? So when it's acting onto an object, it's acting on an object which is where. Okay, so that is going to give you a hint as well. 6.2, a man is pushing a box of 25 kilograms to the right. To try and move the box as indicated in the drawing below, the coefficient of static friction, which is mu s, between the box and the surface is 0.2. Here's the guy. Constant velocity right there. Trying by all means to move a 25 kg box. Okay, let's find the questions. The box does not move. That means it's applying not so big force. Okay, 6.2.1, draw a label free body diagram. So all the time, for you to know how many forces that are acting onto an object, there's got to be a free body diagram. Okay, so this is just very important. Calculate the normal force exerted by the floor on the box. Okay, calculate the maximum force that the man must apply before the box could start moving. This is a nice one, and I know you'll enjoy all of them, just like we did do all of them today. Okay, so this is just a sum up of everything that we have done on mechanics. Hence, today we're just looking at the revision for mechanics. Okay, hope you find it fun. Hope you enjoy doing it. Hope you enjoy calculating. Hope you took all the strategies that I've given you guys. And remember, it's always seem impossible up until it is done. So it might look impossible, but believe me, once you climb that hill and then you look back, it will be like, I'm actually done. I actually know this content. I'm actually good at mechanics. Okay, so keep doing it and have fun. Thank you.